Can everyone hear me in the back? Is it okay? Okay, great. Yeah, I'm going to keep my mask. Yeah, yeah. I give a class to 600 students, freshman students, and I prefer to keep my mask with everyone around, just so that I don't infect you. Okay, let's get started. I think Hussam gave a great introduction to what I'm going to say. I should mention that I have had only 3 hours of sleep in the last 72 hours. So this could be an interesting talk. I should also mention that I gave a 5-hour tutorial on the subject a week ago at Samos, in the beautiful Samos Island. So you can see that these slides can actually be extended to cover 5 hours, 5 days, or 5 minutes. I'm going to try to keep it to 50 minutes or so, but please feel free to interrupt me at any point and ask questions. We can certainly go further. Okay, so I think more than anything else, I would like to set the mindset. Basically, I should say that what we're doing is, let's say, what we're doing in the design of our computers today is not very good. As Hussam mentioned, we have a huge energy and performance problem, and we are exacerbating it. We're making it much worse. The question is, how do we solve it? So basically, the problem today is computing is bottlenecked by data. Important workloads that we have are all data intensive. They require rapid and efficient processing of large amounts of data, and data is increasing. We're generating much more data than we can process. In my perspective, we can build devices that are great data generators. I'm going to show you some example of data generators very soon. But our data analyzers are not very good. We're moving data all around the world to analyze the data, and that's causing a lot of problems, performance problems and energy problems, and sustainability problems. And today we want much more sophisticated things on the data that we generate. I don't want to dwell on this picture a lot, but clearly neural networks, AI, machine learning workloads are driving part of this. Their memory requirements are increasing exponentially. Their compute requirements are increasing exponentially, and you can read papers about it. You can actually watch talks about it. This is a talk that was delivered by the chief architect of Cerebras Systems. We're actually doing memory and compute together in a single wafer scale chip, which is actually, I think, a very interesting direction. So that's AI, but there are many, many other workloads. The world is not just machine learning. In fact, maybe we're doing the wrong thing in our machine learning systems today by relying on so much data. Maybe we should cut back on that and think differently in terms of the algorithms, right? But other workloads are also quite intensive. These are some example workloads. You can look at the references over here. They're all shown to be very intensive in terms of memory, and they demand a lot more memory in terms of they're bottlenecked by memory latency, bandwidth, capacity, sometimes all at the same time, basically. And data is essentially a performance energy bottleneck in them. If you look at the mobile end, these are some example workloads that we're exercising right now, actually, a lot of them. On Zoom, for example, that video playback and video capture is happening. You use your Chrome browser, TensorFlow Mobile, etc. But data is also a performance energy bottleneck in these workloads. And if you look at some future workloads, genomics is an area that we work in. This is actually even more scary, let's say. In genomics, we can generate a lot more data. And clearly, the importance of genomics is very clear today, especially after the COVID-19 outbreak. Basically, we have great data generators in this workload. These are sequencing machines. They're extremely good, actually, at what they do today. But scientific discovery or medical advancements are limited by the speed at which we can process that data and the efficiency. I'm going to show you examples of those data generators very quickly. This is an example. This is actually an old example. It fits in your hand. This can sequence your genome or the COVID-19 RNA, whatever you wish. This device was actually shipped all over the world to understand the COVID-19 variants, etc. Unfortunately, this device is extremely good at sequencing your genome, but it's very bad at analyzing anything. So you have to move the data to at least a phone or a laptop, more likely a data center, to actually process the data that's coming out of that. As a result, your computation is bottlenecked by the data movement. And if you're interested, you can read this paper that we wrote a few years ago that talks about it. So there is a huge performance energy bottleneck for these devices. I think the big picture looks like this. This is an example of genome analysis. We have these special purpose machines for data generation. In this case, it's a sequencer. But you can think of it as video analytics as well. Video is everywhere today, right? Or clicks on the internet, right? These are data that's being generated. We are basically very good at generating data, but our machines are really bad at processing that data because we need to move that data at both the micro scale as well as the macro scale. So this picture is really similar for many data generators and analyzers today. So I like genomics. We actually do a lot of work in this area. If you're interested in it, I'd recommend looking into some works like this that provide an overview. Basically, we need to accelerate so that we can actually keep up with the data generation that's happening. And clearly, there are some systems, in-memory computing is one of them. I'm going to talk about that. But I will mention this just to give some motivation in terms of the results we can get. Earlier in the keynote, Mark Papermaster was talking about improving energy efficiency, right? I think we would really like to improve both performance and energy at the same time. We should not really run into a trade-off between them. And I think the question is, how do we get there? This is an example of how do we get there. So we did this study with IBM, and this is based on real systems. You have a high bandwidth memory-based FPGA board. It's a near memory compute engine, essentially, because it has low latency, high bandwidth connections to this high bandwidth memory. And if you can offload genome analysis to the FPGA board, as well as some weather modeling in this particular case that we did, you can gain very significant performance and energy efficiency improvements at the same time, basically. There's not a trade-off. Performance and energy efficiency improves at the same time. Of course, I'm not going to go into the details of how we do this. You can read the paper for more detail. But this is existing technology. In a sense, it's boring, right? We're system designers and architects. We want to look into the future technology. The question is, what is the future technology? Okay, so I will not bore you more with the genome analysis. I think this is a fascinating subject, but we don't have time for it since we don't have 5 hours today. But I will mention this actually in a little bit, talking about what you can do in the storage system. If you're interested, there's a lot of information out there, and this is a very active area. How do we accelerate genome analysis so that we can give a device to a doctor or a private person as you, and you can do your own genome analysis and actually get answers to critical questions about your health, about your, or the doctor can get an answer to a critical question about what kind of drug they should administer to a critically ill infant, for example, very quickly. Today, we're not there yet. We really want to reduce that to 1 minute, a few minutes. Today, those analyses, some of these analyses take 2 or 3, 4 days. Unacceptable, basically, in some cases. Some cases they're acceptable, but maybe if you reduce that, you can find even better treatment methods. So future is actually even more, let's say, edge-oriented. As you can see, these are some newer devices. But again, they're better. We're building better data generators, but they're not analyzing data. Okay, there's a lot more information on the web that you can find out, and we cover it in our computer architecture classes that are all available. So I gave you some example applications, right? These applications are all pushing the boundaries. They're going to push the boundaries even more. And we'll never be at a point where the applications are not going to be there. We'll have a lot more applications. And unfortunately, they're overwhelming our machines. I will show you with some evidence soon that our storage and memory capability is overwhelmed, our communication capability is overwhelmed, and our computation capability in the end is overwhelmed. We're designing better machines than before, but they're not really doing computing. They're basically idling because they're waiting for data to come back from memory. And data actually greatly impacts robustness, energy, performance, and cost as well. So if you go back to the fundamentals, you really need 3 key components to build a computing system: computation, communication, and storage and memory. And if you look at the history of computing, we've heavily optimized this computing unit. Everything has to go there to be processed, and everything else cannot do much, basically. And computing unit can be today, it's very sophisticated, right? It's very heterogeneous today. It's CPUs, GPUs, FPGAs, machine learning accelerators. The AMD picture that you saw in the keynote this morning is all about the computing unit. It didn't mention anything about the communication and memory storage. It feels like I'm picking on AMD, but that's the state of the world today, unfortunately. So let's take a look at that computing unit. This is the computing unit. This is my cartoonish picture. If you look inside it, computation is a very small part of it. Those red parts, cores. Everything else is there to store and move data. Caches interconnect, other caches, other interconnect, memory controls, other interconnect, other caches or memories, other interconnect, storage, other interconnect. You can keep extending it to the data center also, etc. Basically, most of the system, more than 95% of the real estate of a single node is dedicated to storing and moving data. Yet we call these computing units. Yet the system is still bottlenecked by memory. I'll show you exact numbers soon. Okay, if you don't believe my picture, this is AMD Ryzen. You can see that green box over there. Most of it is caches, SRAM. And I didn't even circle the memory controller, interconnect, other caches, etc. And this is just the computing part of it. Okay, and we keep adding more and more. This is 3D stacking. It's great, actually. It's great to look at these technologies, but at what cost should be our question. We're adding these caches. This is a 64 megabyte cache, 3D stack. What kind of carbon footprint are we adding? Picking on Hassam's talk earlier, by just extending this caching hierarchy over and over and over and over. And you can find information about how much performance the 64 megabyte cache buys you. Not a whole lot in the grand scheme of things. I think it's great to look at the technology though. Okay, not picking on AMD, IBM has very similar designs. You can see that most of it is memory, SRAM. If you look at a little bit system level picture, it becomes actually look like this. Basically, this is a computing chip. A lot of SRAM is a very good approximation of what it looks like. Mostly SRAM, I would call it. And the rest is DRAM. And then I am not even showing you the storage over here. So this is the system we're designing today. The question is this the right way of going forward? This is the system we're designing today. We're dedicating most of our resources to memory, but memory is actually consuming almost a significant chunk of our energy. This is data that we collected with Google across all of these 4 workloads. These are not the most intensive workloads in terms of memory. Still, more than 60% of the entire system energy is spent on data movement in these workloads, just moving across the memory hierarchy, because everything has to go to the computing unit, right? Okay, going forward, I can give you a little bit more data. I'm going to give you a little bit more data also, but let me pull back. I think we would like to design intelligent architectures going forward, because these architectures are going to make decisions for our lives in just self-driving cars, planes, etc., whatever. They're going to be very important for us, right? So the question is, what is an intelligent architecture? I think this is a very philosophical question as well, but if you try to make it a little bit more scientific, I think an intelligent architecture needs to handle data well, most importantly, because data is the most important thing that it's dealing with today. And I think there are 3 major directions over here. We need to ensure data doesn't overwhelm the components that we're designing. This comes with intelligent algorithms, intelligent architectures, intelligent devices, and whole system designs, basically. I think this is very synergistic with what was discussed earlier. We all need to look at the entire stack. I'm going to talk a lot about this part. This is a part I call data-centric computation. But I will mention 2 other things that are also very important that I don't have time to focus on. One is we need to design architectures that are fundamentally intelligent, meaning if you look at the architectures today, there's a lot of data that flows through the system, and the architecture is fundamentally not capable of learning. So it doesn't improve its architectural and system level decisions, basically. It has controllers that are designed by humans. These humans have dictated some policies inside those controllers. These controllers could be the memory controller, for example, the cache controller, the scheduler, etc. There are many, many controllers that we have. And they're doing exactly the same thing they're dictated to do, regardless of all of the data and experience that has flowed through the system. Basically, they don't learn from experience. I would argue that you would not call this intelligent. As human beings, for example, I interact with the environment and I learn from experience, right? I put my hand on a hot stove, I figure out that it's hot, I don't do that again. I think we need to fundamentally rethink our architectures to be learning agents, not just the design of our architectures. Machine learning should not just aid the design. I think that's obvious. It should aid the design of the architectures, but also the architecture itself should be capable of learning. As it ages, it should become better. I call this data-driven architectures, but we don't have time to talk about it. But I think it's very synergistic with data-centric earlier. The third direction, it's also distinct. There's a lot of data that we're dealing with, and data has a lot of properties. If you think about data, it has privacy properties, security properties, compressibility properties, approximability properties, error tolerance properties, locality and performance properties, criticality properties. You can keep adding to it, basically. There's a lot of semantic information about data that floats around that could be discovered. Some of it is discovered, but certainly not much of it is communicated to the underlying architecture, to the hardware. Basically, the hardware and the algorithms do not know about the characteristics of the data. As a result, they make component-aware decisions. I'll pick the example of a memory controller. When you design a memory controller, for example, the decisions the memory controller makes are about components. Is this bank busy? Is this bus busy? What is the row? What is the ID address of the row that's open in the bank? Based on that, it makes a scheduling decision. It doesn't make the scheduling decision thinking, is this request more critical to the user? Is this request more security critical so that I should isolate it so that I don't create side channels? So this sort of semantic information is missing. We don't communicate to our systems. So these two, the last one I called the data characteristic aware architecture. So this summarizes basically what we're doing with architectures today. Today, we're very processor-centric as opposed to data-centric. I'm going to talk about that a lot. Today, we're very human-driven in the design of our controllers as opposed to data-driven. We don't learn from experience. I'm not going to talk about that. And today, the controllers, the systems we design make component-aware decisions because they don't have enough information about the semantic properties of the data. But we should move to a state where we're making decisions based on the characteristics of the data. And I call this data aware. So I think this is really a blueprint for fundamentally better architectures, but we don't have time to talk about the second two, so we will talk about the first one. But regardless, I think we really need to revisit the entire stack for all of these directions. But I believe we can get there step by step, and hopefully I'll give you some directions, and hopefully the earlier talk and maybe the later talk will also give you some example steps that we can take toward really re-examining the entire stack in the end. Okay, I'm going to skip the slide because it says essentially the same thing. I mean, if you're interested, there's a position paper that we wrote on this topic that's only 2 or 3 pages that talks about this direction. So let me jump into data-centric. Once you jump into one of these directions, it opens up a whole new world, basically. What is data-centric? I think even a data-centric architecture needs to have multiple properties. First of all, we need to process where data resides. We should not think processor-centric. We should basically think of the system as an intelligent agent that can process the data wherever data resides, not just in the processor or the accelerator, whatever that is. We should also enable low latency and low energy access to data. This is critical. This, I think, also thinks about emerging technologies as well as architectures, but I won't have time to talk about that. We should think about low-cost data storage and processing and intelligent data management. I will mention this intelligent data management, especially intelligent control is handling robustness, security, cost, and performance. That's going to be very important going into the future. But I will not talk, sorry about that. I will not talk much about this low cost and low latency aspects. But these are all research directions, actually. If there are people here looking for research directions, I think there's exciting research to be done in all of these directions. But let's jump into the first one, processing data where it makes sense. This is the data-centric or memory-centric computing. And I say where it makes sense because today we have no option. We have to move the data to the processor or the accelerator. Let's have options in the entire rest of the system. It could be the main memory. It could be the storage device. It could be the interconnect. It could be the controllers that are controlling them. It could be the caches even. And maybe even the register files, right? If you think about it, the register file and computing is decoupled today also, right? So we should really enable computation capability in all of those. And this is not a new idea. This is an old idea. These are some seminal papers. If you find older papers that are actually crisp enough to actually discuss the idea, I'd be happy to learn about them. It was called Logic in Memory. And this is Harold Stone's paper 1 year later, but it was done around the same time that talks about the same. So what is different today? Okay, maybe I'll animate this. So what is different today is, today we have, in my opinion, no choice. We're kind of getting squished in the middle and crushed. And the things that are crushing us is technology on the one side and applications and systems on the other side. Technology is not scaling very well. As a result, memory is a huge bottleneck. I'm going to talk about that. There are lots of scaling issues that demand intelligence on the memory side. And on the application side, we have a huge bottleneck again. Data access to major bottleneck systems are energy and power limited. Data movement energy is much more than computation energy. And I think I should emphasize this. We need all at the same time, performance, energy, sustainability, scalability. We want all of them at the same time. We don't want this to be a trade-off, basically. I think the key is we can improve all metrics by minimizing data movement. So today's designs are squeezed in the middle. That's why we have no choice, in my opinion. So let's take a look at these two different aspects a little bit. I will talk about push from technology, from the memory technology scaling side. I will not spend a lot of time on this, but I think this is really important also. Basically, today, technologies are not scaling very well. We should look at emerging technologies. I'm going to mention that. But the main technology that we design in all of our systems, DRAM, is not scaling very well. As a result, industry is now finally open to new architectures. I'm going to give you some examples of that. So this is some examples in the old times. If 3D stack technologies are actually going to be a lot more important going into the future. And people are actually experimenting with experimental devices. If I were giving this talk 2 years ago or 3 years ago, this would be just a picture. But more recently, people have been actually developing commercial processing and memory architecture. This is a DRAM architecture with processing units, general purpose processing units inside it. the UpMem company. More recently, Samsung has introduced machine learning accelerators inside the DRAM chips. And this year's ISSCC, SK Hynix introduced very similar machine learning accelerators inside the DRAM chips. Samsung and Facebook introduced memory modules that can do recommendation inference. And again, this year's ISSCC, Alibaba introduced machine learning or recommendation system accelerators inside the DRAM chips. So clearly, there's a push from technology scaling as well as applications that is driving this. But let's talk about the technology. And there are many other experimental chips and startups. You can see a lot of papers also, academic papers. I'm not mentioning them over here clearly. I will mention that a little bit later. So one of the reasons for this push is technology scaling. And technology scaling has always been an issue in DRAM for about 20 years, let's say. But it's become much worse recently. And we've delivered some talks about it. You can find them online. I'll give you one example. This is a study that we did with Facebook some years ago. We analyzed all of the memory areas that they have in their systems, all of their data centers, and we find this curve. This basically shows the correlation between the chip density, the DRAM chip density that's employed in a server and the failure rate in the server. You can see a very strong positive correlation. As the DRAM chip becomes denser, the server fails more often, let's say. Why? Because the cells are smaller, cells are closer to each other, memory cells. As a result, they're much more vulnerable to noise. So there's a lot of reliability issues that these DRAM cells have in the field as reflected by production data center servers, you can see. And you can read that paper if you're interested. That's not the only issue. Today, you can induce predictably errors in most DRAM memory chips. This is the RowHammer phenomenon in DRAM. How many people are familiar with RowHammer? Okay, how many people are not familiar with RowHammer? Don't be shy. Okay, that's good. I will briefly mention it. I don't have time to talk about it in detail. But this is a huge technology scaling issue in DRAM. Basically, the problem is that there's read disturbance in DRAM. Whenever you read a row, activate a row, because cells are too close to each other, they interfere with each other. So in DRAM, it demonstrates itself as what's going on as RowHammer right now. You activate one row, apply high voltage to that row. Let's assume you want to read something else. You deactivate that row. Now, if you keep doing this, activate the row, deactivate, activate, deactivate, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage. It turns out the cells that you did not even touch get corrupted in DRAM today. And that's the idea of RowHammer. And this is read disturbance. Clearly, this should not be happening. We're not even writing to memory. Nothing should be changing in memory, let alone the cells that you're not dealing with. These could belong to some other applications. These could belong to the operating system. As a result, it's a reliability issue, but also security vulnerability. And most DRAM chips are vulnerable to this, even today. And this is a scaling issue that's becoming much worse today. If I had time, I'd be happy to talk about it. But clearly, people have developed a lot of security attacks based on this. And this is a big issue in the DRAM industry right now. And people are actually developing solutions that put intelligence inside the DRAM chips to solve this problem. That's the argument for intelligent memory controllers. And DRAM, if you know the DRAM industry, they would not put anything into their DRAM chips that would hurt their density, right? But they're doing it today. So there's some intelligence in the DRAM chips that tries to detect these RowHammer attacks, activations, many activations. They don't work perfectly, but it's getting there. Okay, so if you're interested, there's a lot more in this area. In fact, it's a very hot topic right now. It's still going on. How to solve this problem in an efficient way is very interesting, I think. And you can find information about it in the papers that we have written, as well as the talks. And there are many people working on this topic. Okay, let me give you another technology scaling issue. This is related to emerging memory technologies. If one technology is not scaling very well, why not have multiple different technologies put together and then design intelligent controllers that can allocate the data and move the data such that you can achieve the good of each technology as much as possible while avoiding the bad of each technology as much as possible. That's the idea of heterogeneous hybrid memory systems. And that's already happening also. This controller needs to be intelligent because it needs to understand the device characteristics. It also needs to understand the application characteristics so that it can allocate the data nicely. And this could be different technologies, clearly. This could be also different types of DRAM. Okay, let me give you, I think I could keep giving these examples, but it's clear that we need intelligent controllers in main memory going into the future. And this is an example of intelligent control. There's a lot of literature out there looking at these intelligent controls. This is a secure solution to RowHammer. It comes at a cost, though. So industry is also writing papers about it. If you're interested, I recommend this short paper that was written by Samsung and Intel in 2014. These are two companies that don't normally talk to each other, but they did write this paper. And they basically said DRAM process scaling is becoming very difficult. So we should really architect controllers and DRAM together and have intelligent controllers, essentially. And there are many other example intelligent controllers in our research. I will mention this because we actually see this over and over in different memory technologies. It's not just DRAM. Flash memory actually has a lot of issues in terms of reliability and scaling. As a result, people have quickly figured out that we should design intelligent controllers for flash memory. And these are actually quite intelligent controllers. There's a lot of literature out there. And if you're interested, we have written this overview article based on years of research that we did on this topic. But I'm not going to go into that. There's, I think, a lot of similarity in different technologies. And if you say that emerging memory is not vulnerable, I think good luck finding a technology that's not vulnerable to these effects. This is phase change memory, but there are other technologies that have similar reliability and endurance issues. So there's always some issue in technology, memory technology that scales to smaller dimensions. So you really need to design intelligent controllers. And I think the takeaway is that intelligent memory controllers can avoid many failures and enable better scaling. That's the technology direction. Let me now give you the systems and applications direction with some data. I would argue that it's going to be even worse. So if you thought technology direction is worse, I think our application and systems direction is even worse. Basically, I've already said all of these. Let me give you a bigger perspective. So the question in my mind is, do we want a world that looks like this? I think Hussam gave you some numbers, like 13% of the entire carbon footprint will be based on data centers. I think it's kind of unacceptable to go into that direction. Some other projections show maybe 30% or something like that. I don't think we want to go there, basically, because that will be a very bleak world. But I think we are greedy also. We want high performance, energy efficiency, sustainability all at the same time. The question is, can we actually do something that could get us there or closer? And I would argue that yes, basically, the first design decisions that we make in our systems is really causing great energy waste and great performance loss also. And that's the processor-centric paradigm. We know that data movement is performance intensive. Basically, there's a lot of latency, and it costs a lot of energy, clearly. I put great performance loss in parentheses because we actually add a lot of things into our systems to overcome the performance overheads or latency overheads of data movement, right? We add massive levels of multi-threading, huge cache hierarchies that I showed you, and we keep adding and adding and adding and adding. Out-of-order execution, huge levels of out-of-order execution and prefetching. If you look at the memory hierarchy, it's very complex, actually. And most of it is there, actually, to tolerate the data movement. Now, the problem is, when it works very well. But when it somewhat works, it's wasting a lot of energy. And it's also adding a lot of complexity. And there are many applications when this memory hierarchy doesn't work today. I'm going to give you some examples soon. For example, imagine a random access application. Most of the things that we do in our memory hierarchy today doesn't work, basically. It exacerbates the energy waste, it exacerbates the performance loss. So we're in a vicious cycle today to overcome the performance overheads of data movement. We're adding a lot of complexity to our systems, 3D complexity to add the caching, for example. I showed you the examples. That's causing even more energy waste. So basically, we're increasing our energy waste because data movement is fundamentally energy wasteful, but we're adding to it that energy waste. The question is, can we get out of this? And I think getting out of this is really realizing that the problem is that we're very processor-centric today. And this picture that I showed you over here repeats itself, let's say. I already said this, so I'm going to skip this. Now, let me give you some data. We know that memory is a problem. We should do something about it, I think. This is a quote from Dick Seitz, who was the chief architect of alpha processors. And after they designed the flagship alpha processor in 1990s, he wrote this one-page article, which I would recommend everyone to read. And he basically said that we designed this flagship processor to finish 4 instructions per cycle, per clock cycle. And it's capable of doing that. Unfortunately, in this important database workload, which we thought that we designed this processor for, it's finishing 1 instruction every 4.7 cycles. So it's operating at less than 5% of its peak bandwidth. Why? It's waiting for data to come back from main memory most of the time. And he finishes the article saying this is a direct quote. I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, fast forward 10 years. This is data from my own PhD thesis. We worked together with Intel to analyze the applications and the processors, cutting edge processors at the time. And we found out that we found out the same thing, basically. Most of the time, the processor is waiting for data. This averaged across about 150 applications. Okay, if you don't believe me, if you don't believe Dick Seitz, even if you read my first paper, maybe you'll believe me, but fine. Since everybody believes Google, Google publishes the same data about 10 years later. This is all of their data center workloads, as you can see. Most of the time, the processor is in the red domain, which is waiting for data to come back. It's finishing instructions. Basically, it's doing useful work only 10 to 20% of its time. Remember, this is the processor that we showed earlier. Most of it is really storing and moving data. Apparently, something is not working. And I could keep giving these examples. Sometimes this number, this red part goes up to 99%, in especially some heavy, intensive machine learning workloads. 99% of the time, you're waiting in an optimized accelerator even. Okay, so I think I don't want to harp on it more, but basically we have a huge grossly imbalanced system. Processing is done in only one place. As a result, data moves a lot. This is energy inefficient, low performance, and complex. On top of this, we compound the complexity, and this makes it even more energy inefficient, low performance, and complex. And we have this picture that I showed you earlier. Most of the system is dedicated to storing and moving data, but the system is still bottlenecked by memory, as we saw. Okay, that was the performance perspective. Energy perspective is even worse. If you look at energy, this is data that I borrowed from Bill Daly, chief scientist at NVIDIA. This is old data, but the trends are very similar. A complicated double precision floating point operation, 20 picojoules to do that operation. A DRAM, a memory read or write, 800x higher energy. Okay, 800x, you can optimize it. You can get down to close to 100x, but you cannot get down to even more than that in DRAM today. So basically, we're 2 to 3 orders of magnitude worse in terms of energy when we access main memory. And I think this is, actually, this picture is a success of technology scaling. Technology scaled really well for transistors. It did not scale very well for interconnects and memory devices themselves. As a result, over the course of 70, 80 years, the transistors became much more efficient, but interconnect and memory device did not become efficient. That's why we're actually paying the energy penalty right now. Now, if you look at this picture, it's a good idea to ask the question, assuming I have a huge cache hierarchy, how much locality should I have in my data to actually not pay this energy penalty, to amortize the energy cost of the data moment? And that number is actually very large. You need to reuse the data many, many times, sometimes more than 1,000 times to actually overcome this energy cost. I'll leave that to you. Wen-Mei Hu from Illinois actually has a very nice calculations in his talks that talks about it. Okay, that was a complicated arithmetic operation. A simple arithmetic operation, a simple integer add, is much more energy, let's say, much more energy efficient. As a result, DRAM energy is much higher comparatively. And you can read the papers that talk more about this. As a result, we have systems that are just moving data around, and the energy is consumed on that data moment, more than 60% of the energy. And I would argue that these numbers are more average in many very intensive workloads. These workloads that we examined were intensive, but not that intensive. They're very intensive machine learning workloads that push the number to 90%, 99%. So I would argue that we do not want to move data in this domain. We need to really enable computation with minimal data moments, compute where it makes sense, enable options basically in the entire system, and make computing architectures more data-centric. And I'm going to give you more examples from main memory at this point, and some storage as well. But main memory is very interesting, but we should really do this across the entire system. Main memory is very interesting because today we're actually capable of building very large-scale main memories. And we actually, application designers put applications so that they try not to go outside the main memory, right? There's in-memory databases, in-memory graph analytics engines, in-memory media processing, in-memory machine learning frameworks. So we should take advantage of that, especially in main memory. And with emerging technologies, this becomes even better because your main memory becomes even denser. So you can actually put more into the main memory. So basically, we would like to be able to say to memory, can you give me the results of this query? And the memory gives the results back. So we're going to treat memory as an accelerator, at least in the short term. But in the longer term, memory actually could be capable of being a fully independent device as well, independent computing unit. So clearly, there are many questions, even if this is an accelerator. How do you design the memory and the controllers? How do you design the processor and communication units? How do you design the software and hardware interfaces? System software compilers and languages, algorithms to map to the devices over there, and theoretical foundations. This is really an across-the-stack problem. And in fact, I will mention this theoretical foundation since not many people are looking at it. If you think about the theory of computing, that is very processor-centric to begin with. So if you have taken a complexity of algorithms class, you're counting operations. The big O notation, big theta notation, they're all about counting operations. They're not about data at all. But as we just showed, it's all about the data. So maybe the theory that we have for computing is today not very satisfactory for what we need going forward. And I think this is very important. Basically, we really need to rethink the entire stack, including the theory. Okay, now I'm going to give you some examples in the remaining time. We write overview articles, and this is something I would recommend for people who want to go into this topic. This covers a lot of history as well as emerging topics in processing in memory. Now let me jump into, but we do need to think differently from past approaches. I think thinking differently also requires categorizing what we're doing as well. I'm going to try to clarify the terminology for processing in memory into only two categories, because I think there are two fundamental categories. One is processing near memory, the other is processing using memory. And I would like to distinguish them, but I will start with processing near memory because that's the easier thing to do, let's say. So what is processing near memory? Today, processor is here, memory is here. You can think of it that way. Let's put processor or logic, accelerated logic, closer and closer, closer, closer inside the memory and couple them together as much as possible. Now, logic is getting near memory, but you're still designing logic, right? As we're designing with processors today. So that's easier to do. It doesn't fundamentally change the programming model, for example. That's why this is already happening in the field. Processing using memory is fundamentally different. It's similar to what Hussam mentioned, emerging technologies. If you think of a memory device, today we design it as a memory device, but the memory device actually has computational capability in it. That's the realization over here. Can I take a memory device and use it for computation? And can I actually make it better for computation also? So can I use this memory device to perform computation? And I think this is fundamentally different. You need to rethink how you actually do your algorithms so that your algorithms map to this device so that you can do XNORs, for example, or majority functions, as I will show you if I have time. That's why this is going to be longer term, in my opinion. Okay, let's start with processing. But in both cases, the mindset will be that we should use memory as an accelerator to begin with. Memory is good at doing something. Let's accelerate things on the memory side. Okay, so let me start with this processing near memory and give you some example application and hardware co-design studies. So when we first started looking into near memory processing in 2011 or so, we wanted to look at applications, and graph analytics was a really important application. Clearly today it's very important also because we have huge graphs that we're dealing with. And this is fundamentally memory bound. Basically, if you throw cores at the problem, you don't gain a lot of performance, and efficiency actually goes very bad. Why? Because you have a lot of random memory accesses and a little amount of computation. You're memory bound essentially. And we wanted to look at designing 3D stacked architectures that actually fundamentally eliminate the data moment as much as possible. So 3D stacked architectures, you have a logic layer under memory layers, and logic layer can have high bandwidth, low latency connections to the memory layers, and you can put computation units into the logic layer. So this is the system we designed for graph processing. I don't have time to go over this because it's an entire system design, but we start with this cube. In the logic layer, we have what's called vaults. We divide into vaults. Each vault has a memory controller as well as an in-order, very simple in-order core because there are thermal limitations and area limitations. And in-order core controls the memory on top of it. And then if you want to scale the system, you actually replicate these cubes with some interconnect. And you connect it to a host processor. So it's an accelerator for graph processing. What you do as a programmer is you map your graph on top of these nodes and inside the vaults also. And hopefully you partition your graph so that you have some locality. That's going to be important. The communications, you don't move the data. The data stays where it is. Whenever you want to update the data, you send the function to the data and the intermediate results that you want to add, for example, or update the data with. So data movement is minimized. So fundamentally, it's a remote procedure call-based programming model. It's very similar to a distributed system-based programming model that we employ in data centers today. And we have a lot of other mechanisms that I don't have time to talk about. But if you think about this, you offload your graph computation and it accelerates your graph computation without moving the data, by trying to minimize the data moment as much as possible. That's the idea. And we compare this to existing systems at the time. You can see that all of the existing systems, the state of the art, this is the cutting edge systems, have a dichotomy between memory and the processor. Tesseract is different. You can see that there's no memory and processor that you can easily distinguish because they're coupled with each other. And you can see that the memory bandwidth that's available to the core is much higher at the time. Today, it's much higher, of course, but even at the time, this is 2013 or so when we actually got the numbers. And as a result, the applications improve significantly. Performance improvement on applications is more than 13x on average across 5 different graph processing algorithms. And this is our work. Many later works built upon this work, and they actually optimize the system. They tried to get better out of the system, and this number went up to close to 100x, more than 100x today. Energy efficiency at the same time reduces by 8x according to our results. Existing work shows that this also goes down by 2 orders of magnitude. And it's not a trade-off. You improve both performance and energy efficiency at the same time. So I think the number AMD was giving was maybe 1000x energy efficiency improvement. If you multiply this energy, it's not energy efficiency. If you multiply 100x performance improvement and 100x energy, that's more than 1000x on this application. But this is general purpose because it's not specialized to graph processing at this point. Okay, if you're interested, you can read more about it. Let me give you another example, more recent example from the storage system. This is work that we published at ASCLOS this year. And this is, again, specific to genome sequence analysis. And if you look at the data movements, actually data movements is a lot from the storage system also. So you move genomic data from the storage system all the way into the computation unit. Today, we try hard to eliminate the computation overhead. We basically design a lot of accelerators, heuristics, filters, etc. So computation overhead reduces. Data movement overhead comparatively increases because of this. Computation is actually, as we improve the computation, data movement becomes a bigger bottleneck, basically. So how do we improve the data movement overhead? In this particular case, we decided to add filtering mechanisms in the storage system. So add a little bit of logic into the storage system such that it's intelligent enough to filter reads quickly. And this way you can actually filter a lot of reads. Very small amount of reads, fraction of reads, or genomic data needs to go to the computation unit. Everything else can be handled by the storage system. And I'm not going to go into the details because we don't have time for it. The key question is, of course, what do you filter out in the storage system? This is very application dependent at this point, but I don't have time to go through it. But I will give you the results. Again, this is not a trade-off between energy and performance. Performance and energy improve at the same time. And the numbers can be very large depending on how much filtering you can do in the storage system. Okay, if you're interested, there's more in this direction. Let me give you some more examples. So this is the study that we did with Google. We wanted to understand the data movement in these applications. And I already gave you one of the results that we found. More than 60% of the entire system energy is spent on data movement. The question is, where does the data movement come from? What kind of functions? And we found out that data movement often comes from very simple functions. So if you want to be very frugal in what to do on the memory side, you should really identify these functions and design logic on the memory side. It could be simple low power cores. It could be specialized fixed function accelerators. It could be reconfigurable logic. In my opinion, it has to be heterogeneous also on the memory side. And offloading those functions gives you actually significant performance energy improvements, again, at the same time, not a trade-off. Okay, I don't have time to talk about it, but clearly there are some functions that are more important than others, and you can read the paper for more detail. And they exist in all of these workloads, actually. Okay, so there are a lot more examples that I don't have time to go over. GPUs actually have similar examples. You can identify some functions that are important to offload to smaller GPUs in the logic layer in near memory processors. And you can accelerate pointer chasing, and I don't have time to talk about more of this. So this is actually very interesting. Time series analysis is also very data intensive. Okay, let me give you one more example. Hussam talked about TPUs. This is actually very interesting. TPUs are designed very inefficiently today. This is another study that we did with Google recently. I will give you the summary very quickly. We studied basically proprietary edge neural network models that Google uses in their edge devices. And we found out essentially the edge TPU, that's monolithic accelerator, doesn't work very well. Because it's the picture that I showed you earlier, most of the time it's waiting for data to come back from memory, even though it has a very strong computation engine. The key idea over here is that why don't we design heterogeneous accelerators? Some of them are data centric and some of them are compute centric. And if you actually do this, the performance energy improvements that you get are significant at the same time, 3x and 3.1x on average across these models. You also improve the area efficiency of the accelerator because you customize. Let me give you some idea of what's going on. So these are the edge models that we have examined. You can read the paper for details, but they're very heterogeneous, as you can see. The parameter footprint that they have is different, and the arithmetic intensity that they have is quite different as well. And this also varies within the model, within different models. So there's a huge variation. So today's accelerators are designed to be monolithic. They're basically trying to cater for all of those models and layers at the same time. the question is, how do we design these heterogeneous accelerators? So the idea over here is that you figure out different families of models and design accelerators for different families. And it turns out many of these families are very data intensive. So your accelerators need to be near memory, but your accelerator can be very simple compared to this sophisticated accelerator because they're very much bottlenecked by data over here. So in this particular case, we have a compute-centric accelerator and two data-centric accelerators near memory. And we have a runtime that decides which layers and which model should go to which accelerator. So clearly this is more complicated, but in the end, well, you need to identify layer families and design this way. I don't have time to talk about this, but in the end, you improve energy consumption. You can see that especially some models that are not examined as much in literature, SKMs and transducers, these are very much heavily data bound. And you improve energy consumption significantly. You also improve throughput at the same time. And we show in the paper that you improve latency. And not only that, the area of these three accelerators combined together is smaller than the area of the monolithic HTPU accelerator. And you can read more about this in this particular work. How much time do we have? Oh, okay, 0 minutes. Okay, I can accelerate it. I'm not sure. Okay, let me tell you that I think we need to revisit the entire stack basically, and we can get there step by step. So I think these are all case studies that show that there's a lot to be gained. I will not talk about the processing using memory approach, sorry, because we don't have time. I think Hussam gave you an example from the ferroelectric FEFET technology. Similar things you can do in DRAM also. In DRAM, you can have a majority function by doing triple over activation. And you can also have a complement. And if you have a majority, bitwise majority, and bitwise complement, that's functionally complete. And you can map your algorithms to that bitwise majority and bitwise complement. And you get significant performance and energy improvements, again, at the same time. On top of this, in DRAM, you can generate random numbers based on the purely operational characteristics of the device. So processing using memory is all about taking advantage of the operational characteristics of the memory device to do computation as well. We don't add any logic except for mechanisms to enable this computation in the device. So there's no NOT gate we add, there's no majority function gate we add. In my opinion, these two need to be combined. I think processing using memory is great, but essentially not enough. It's not easy to do everything over there. You start with these basic primitives like XNOR or AND or NOT and majority. The problem is if you want to scale that up to, let's say, large data types like 64 bits, 32 bits, 16 bits, it becomes very difficult. And we analyze that in our works, but again, I don't have time to talk about it. So these slides actually talk about it, so you can take a look at the slides, and they're all available. I will mention one thing maybe before we go about this, but some of these operations, you can actually do this in real DRAM chips, existing DRAM chips. These DRAM chips are not designed for computation. Memory manufacturers basically do not provide the DRAM chips, advertise that as computation. But by violating, sorry about this, I don't know what's going on. Right, floating meeting control signs, good. Yeah. By violating the timing parameters in the memory controller, you can do the copying inside the device very reliably. You can also do bitwise majority function inside the device. And bitwise majority, as you know, can be, if you manipulate the Boolean equations, you can do bitwise AND and bitwise OR, right? So you can do this in real DRAM devices today. Random number generation also, you can do it in real DRAM devices. Physical unclonable function, real DRAM devices. In this prototype that we released, you can actually, if you're interested, you can download this prototype and use it and figure out what you can do. This is an end-to-end system prototype that shows that at the application level, you can take advantage of these things. Okay, I will stop with this over here, but maybe, yeah, that's the processing using memory stack. I want to take questions, but before I take questions, I will mention something that's extremely important, and that's the adoption issues, right? So clearly we can build hardware, and I think we can build a lot more hardware. The question is, how do we get it adopted? I think there's a lot here, and that's what our paper is a lot about. So if you look at the paper that I mentioned earlier, 30% of it is about adoption. And there are many, many adoption issues that we need to solve. This is really across the stack. I believe we need to change our mindset to solve these issues. So clearly, application of software, programming, system and security, runtime and compilation, infrastructures, all of them need to be done. This doesn't talk a lot about hardware, as you can see. I think hardware is very interesting. We should do it. We can design very fancy hardware, but in the end, if we don't get it adopted, it will just sit there and it will be forgotten. Right? This is really key. That's why I think we need to think across the stack. And these key applications, the studies that I showed you are really adoption studies, in my opinion. But there's more. We need to keep it simple. We need to think about coherence. We need to think about issues like synchronization, virtual memory. There's a lot to think about. But the good news is, real world actually is adopting some of the hardware right now. So let me give you some examples very quickly. This is the UpMem processing in DRAM engine. They basically have DRAM chips. Inside the DRAM chips, these are real DRAM modules, as you can see. This is a real DRAM system. We've been writing papers about it. Inside the DRAM, next to the DRAM bank, you have a processor essentially. If you want to know more about the processor, you can read the papers, watch the videos, etc. I don't have time, unfortunately, or ask me questions soon. We have released a lot of benchmarks because this is really needed to be for adoption, and you can actually play with that if you're interested. And they're all open source, and we'd be happy to get feedback and also work with you to make this better. And this is the paper that actually talks about this benchmark suite, as well as the characteristics of this real processing in memory system. Let me give you some more examples. I'm going to skip a lot of these. You can find all of these slides. As I said, this was a 5-hour tutorial. So this particular system actually doesn't have a multiplication, a hardware multiplier. If you want to do a multiplication, you need to go through a software emulator. Even then, you get benefits from sparse matrix and vector multiplication. And this is a paper that we published in Sigmetrics this last June that talks about sparse matrix and vector multiplication on a real processing in memory system. I would encourage you to take a look at it. How do you actually do sparse matrix vector multiplication in a system that doesn't have an inherent hardware multiplier? In my opinion, it's not a great choice to not have a multiplier, but even with that, you gain some benefits, even without the multiplier, let's say. Okay, as I mentioned, Samsung has prototype chips with function in memory. You can read more about this also. They have a number of papers. It's an accelerator for, essentially, this has a lot of multiplication inside that chip. So you can see the difference in the approaches for different companies also. And you can read more about this. This is the recommendation system Samsung and Facebook designed together. It's a module level approach, near memory. So all of these are near memory approaches, processing near memory approaches. None of these are using memory approaches, as you can see. SK Hynix has a more sophisticated system, in my opinion, than Samsung's, that also is designed targeted towards these inference applications. And as I mentioned, Alibaba has this recommendation system. These are all DRAM based. You can see DRAM technology is quite strong, and people are building on this DRAM technology to actually accelerate applications. And the future, I think, is going to enable even more, but we don't have time to talk about it. Okay, let me actually conclude, and I'll take questions. Okay, so I think hopefully I'll convince you that we must, and I should really emphasize that must over here, design systems to be balanced, high performance, energy efficient, all at the same time. And that will lead us to intelligent systems. I talked about data-centric systems today, but data-driven and data are extremely important and synergistic with the data-centric system. We should really enable computation capability inside and close to memory and other memory structures that are inside the system, and communication structures as well. This can lead to orders of magnitude improvements, both in terms of energy and performance. And I've given you some examples. Enable new application and computing platforms, and enable a better understanding of nature, in my opinion, also, because I don't think nature is fundamentally processor-centric. And we have a lot of evidence against that, against processor-centric nature, let's say. And who knows what else. So I believe future of truly memory-centric computing is bright, but we really need to do research and design across the computing stack and get over this processor-centric mindset. Basically, this heterogeneity and everything, all of those are great. But we should really get rid of this processor-centric mindset and think more data-centric going into the future. And it's also good to consider like what's inside here. I don't believe that our goal should be just emulating what's inside here, but we can learn from some things that's happening here. Heterogeneity is one example. I think we've learned that, but I don't think we've learned the, let's say, data-centric part of this fully yet. I don't claim that I know everything over here, by the way. I don't think we know everything over here, but we know some things. Let me thank my students over here. Let me thank people who have funded this research. Clearly, there's a lot of research that goes on, and that's most of it is done by my students as well as collaborators. I'd acknowledge them over here. You can read more about them in our newsletters. And essentially, everything that I talked about is available online. We do a lot of open sourcing. You can find open source tools on our GitHub as well. And we have a lot of open source courses. If people are interested, they can join and learn more about this. Specifically, we have processing in memory course where we cover a lot of these materials in depth, essentially. So I will stop here, and I'm happy to take questions.
Very nice talk. One of the problems in memory computation is if you take volatile memories, it's a disturb. Okay, and if you take non-volatile memories, it is related to mismatches quite a lot, right? I mean, around kind of issues and all kinds of peripheral logic that goes inside, including DACs and all the peripheral circuitry, which also has mismatches. So from the accuracy perspective, what is your opinion that which one will have a chance to succeed?
Okay, so I think you're talking mainly about the processing using memory case. You're really using the memory device to do computation. And I agree. I think certainly there's a lot of mismatch, variation, disturb issues, reliability issues. I believe first, clearly there are applications that can take advantage of approximate nature, but we should really build reliable substrates that work also. And that's why people are doing research on that topic, right? So in my opinion, a lot more research needs to focus on the reliability, variation, inaccuracy aspects of processing using memory. No question about that.
Right, but ultimate goal is, it has to get into somewhere, right? That's the ultimate goal.
Yeah, absolutely. But that's why I said processing near memory is the shorter term approach. With processing near memory, you don't have any of those issues, in my opinion. Basically, you put logic inside the DRAM chip, and I think we're capable of doing that. The question is, what is the quality of that logic in terms of energy, leakage, etc. But you usually don't have the reliability issues that processing using memory approach has. So I absolutely agree. It's a longer term approach, and I think we need to figure out a lot to really make the processing using memory approach work. You're welcome. I should also mention that that's one of the reasons why we built that infrastructure for DRAM. So hopefully people can take that infrastructure and look at the reliability issues that they get in real DRAM chips. Unfortunately, it's limited because it's just existing DRAM chips, right? But you can still discover a lot. Please, sorry.
Thank you so much. Yeah, that's a wonderful presentation, the tutorial, so much information. Yeah, I wish I could listen more. Definitely will check out the website. Yeah, I forgot to introduce myself. My name is Jen Ping-Wan from University of Minnesota. And so you talk about the two things really strike me a lot. We try to put the two categories. One is the processing near memory and processing using memory, right? So my group worked on the processing or computing using memory for almost 20 years. I still remember early days when we talked at the device conference. Really, no one understand or care about that. Yeah. And at this time, we might have a workshop to talk about processing using memory. That's wonderful. So, but still, there's some difference in the processing using memory. I think you try using FE fetch, right? All those try to do the processing using memory. So the one challenge, I think, when you do the processing using memory is how can you access the data, right? How can you transfer that results from one gate to another gate? In this sense, the most important part is the gate level design, right? If your gate level design not capable to do those kind of things in terms of random access, in terms of transfer data easily, you're still back to something close to near map. Or kind of like that. So I would like to listen to your comments in terms of processing using memory. Can you go a little bit deeper there? Because finally people start pick this idea, but it still is not pitching on the right, in terms of whether we can have random access the gates, right? Basically the gate flying. So we call that a prime idea, computation random access memory. So we proposed this a long time ago. Seldom attend this conference every 5 years and once. So I'm glad I attended your tutorial. Yeah. Thank you so much.
Sure, thank you. So yes, absolutely. So I think this really depends on technology. I can go into more detail, but we don't have time. I have a lot of slides, but certainly you need to have a way of communicating data nicely between the gates. And this really depends on the technology. I think in DRAM, for example, if you're doing bulk operations, it's easier. You basically move the data to some rows. You still need to move the data a little bit so that you can actually manipulate the data in the way you want. You can actually have a scratchpad space where you actually operate on the data, as opposed to the entire memory array where the data sits. So the way we do it actually is to reduce complexity. We have a scratchpad space, so you move the data a little bit to a location, and then you apply the processing using memory primitives over there. In some other technologies, it's a bit different. You need to really construct the gates and construct the array so that you can communicate the data nicely. I agree that this is a hairy issue. So certainly data mapping and data movement inside the memory is an issue that has to be examined. I don't believe that it's going to be as, so that's one of the reasons why I mentioned you will need to combine processing using memory and processing near memory a little bit, so that, because it's very hard to do everything just using memory. And I think you just pointed one thing that is very hard to do. So if we had time, we would go into more detail, but sorry. Yes, please.
Thanks for explaining this in person. And what is wondering is the energy efficient and optimized is completely explained in the existing discourse, but as you mentioned before, the reliability has also another shift in the DRAM systems. So I was wondering if the DCC like an error correcting process, another logic in DRAM systems, and this like a real DRAM vendors. DRAM vendors have really have another logic in their system and logicized like HBM systems.
So you're asking whether DRAM vendors have error correcting codes inside the DRAM chips?
Yes. Or DRAM chips or DRAM levels or other
Yeah. So today's DRAM chips are so unreliable that DRAM vendors eventually bit the bullet and they added error correcting codes inside the DRAM chip. So the answer is yes. And also the HBM, high bandwidth memory, also they have error correcting codes. And I think going forward, this is another example of intelligence that's driven, well, slight intelligence, error correction, right? Driven by the technology scaling problems. I think going forward, we will see more of this. One issue is, I think we've actually worked on this a lot in error correcting codes. One issue is what happens inside the DRAM chip today. Error correction happens transparently to the memory controller and the system. As a result, DRAM doesn't inform the system when it corrects an error or when it's unable to correct an error. As a result, we run into some issues in terms of overall system reliability. So we need to be, again, cooperating better between the error correction mechanisms that are employed inside the DRAM chip and the error correction mechanisms that are employed outside the DRAM chip. Sure, you're welcome.
From University of Alabama. So you mentioned about RowHammer attack on DRAM chips. Do you have any thoughts on other memory technologies like flash, where one row is very close to the other row? So any thoughts?
Yeah. So I should go back to this. So certainly in flash memory, read disturbance. Okay, let me pull back. Read disturbance is very fundamental, or disturbance in general is very fundamental to any memory technology. And we see it in SRAM, we see it in flash, we see it in DRAM. So in flash, there's certainly read disturbance. I'm trying to find my slides, but I'm getting lost in them. Okay, so this paper is an overview that talks about read disturbance also. So we've done some research on that topic, and there's a lot of read disturbance that goes on in flash. The nature is a little bit different. So whenever you read a row in flash, it's called a page in flash, you basically apply some voltage, and you have to apply very high voltage to all of the other pages in the same block so that you inhibit those cells. And this high voltage that you apply to all of those other rows actually cause disturbance across the entire flash block. And this is a problem, especially when you scale the technology to smaller nodes. There's a lot of read disturbance effect that goes on. And we analyze this. In this paper, we point to some papers that analyze it, but we have a DSN paper, DSN 2015 paper that talk about read disturbance issues in flash memory. Now, it's very similar to RowHammer in a sense, but in flash memory, it's much harder to do an attack, a security attack with this, because there are layers of protection. And flash controllers are handling this. basically. They actually employ multiple different techniques, some of which were proposed by us to actually handle this read disturbance. So fundamentally at the device level, the problem exists, but I think it's much less of an issue compared to DRAM today because it's being handled. In DRAM, I think the downside is DRAM has been expected to work as perfect memory, right? Nobody wanted any errors in DRAM. As a result, we don't employ any error correction in our DRAM system. That's going to change into the future, and it's clearly changing today. That's why the errors that got into the DRAM got directly exposed to the programming language, the operating system, the applications. As a result, this became a huge security issue. But in my opinion, any memory technology is vulnerable to read disturb when it scales down to smaller technology nodes. And you need to somehow prevent it. Sure. Okay.
From this airline, you touched on the adoption of processing memory. If we go back to computing history, in an embedded system, we had a scratch-pad memory back in the 90s, was very popular, but it never been used in HPC or PC or whatever. What do you see as a that you don't go the same path again? What is your thought?
Yeah. So, okay, sure, you're welcome. So I think scratchpad. I'll pick on scratchpad. It was adopted nicely in GPUs, so people used. Yeah, that's right. And yeah, it's not easy, right, basically, to deal with it. I think we really need to focus a lot more on the software stack, for sure. Clearly, it's going to be not easy for the general programmer to adopt everything that we discussed, but we really need to enable the expert programmers to take advantage of the substrates that we're discussing, right? So GPU technology was adopted, right? Because people found benefits out of GPUs. Applications were shown to take advantage of the GPUs in terms of both performance and energy efficiency. I like thinking of the example of GPUs. That's why I think having a data-centric accelerator, in addition to a compute-centric accelerator like GPUs, machine learning accelerators, is potentially a good thing. But yes, I think your question requires more time than we have to discuss.